Welcome to Biochemistry
We're diving
Simplified.
into the fascinating world of bioenergetics, the science behind how our cells produce and use energy to power life. Stay tuned as we break it down step by step, making complex concepts simple and easy to understand. Don't forget to hit subscribe for more engaging biochemistry insights.
Hello, welcome to
Let's get
Biochemistry
started.
Simplified. Good morning, everyone. We're here for another exciting set of lectures on our continuation of bioenergetics. And today we're going to look at our third energy diagram. And just like a quick recap, here we stopped at the last lectures. Is we started looking at spontaneity and we looked at different energy diagram. We took a look at spontaneous as written, that is when your delta G is less than 0, and we saw the energy diagram showing the activation energy and how it looks like, and how energy diagram for spontaneous reaction releases heat as expected, enthalpy, and we also look at energy diagram for delta G is greater than 0, that is spontaneous in the reverse direction. And we saw what the energy diagram looks like and the activation energy, and we saw that it's going to be a positive delta G because the energy content of the product is far higher than the energy content of the reactant. So today we'll be looking at the third energy diagram that shows us the relationship between thermodynamics and kinetics, and that is what we are just going to kick off from. The energy of the reactant in this case and energy of the product is in the domain of what thermodynamics, and the parts in which the reactant takes to go from energy goes from the reactants to product is actually the domain of kinetics. So let's just dive right in and see how the energy diagram looks like. So I'll do this in red, I guess. So you want to draw your energy diagram this way. So here, the energy diagram looks something like this. All right, so at this point, you have your reactant, and at this point, you have your product. At this point, you have your product. Okay, so let me quickly take a different color to indicate that. Okay, so at this point here, like I said earlier, that point here shows you your reactants. So you have your energy here showing you your reactants, energy. And of course, this point here now shows you your product energy. All right, so like I said, this third diagram, it shows the relationship between the domain of thermodynamics and that of kinetics. So the energy of the reactant and the energy of the product is in the domain of thermodynamics, while the path to which the reactant takes place or goes from reactant to product is in the domain of kinetics. So I'll just quickly indicate that here. So from this point down, and from this point okay, so right here you have between this point and this point, you have here thermodynamics, and here that's for this. And here you also have thermodynamics. Okay, so between this point and this point, you have kinetics. So do that in red. So between this point and this point, to show you clearly, you have kinetics. So here you have kinetics. Alright, so we have mentioned before that the term spontaneous refers to thermodynamics. Like we saw in the first two diagram, we are looking at spontaneous at different direction in the reverse positively delta G greater than 0, and at the forward reaction you have um, spontaneous reaction delta G less than 0. Okay, so it actually just refers to the domain of thermodynamics potential tendencies. It has nothing to do with how fast. That's being spontaneous has nothing to do with how fast. It's just what the thermodynamics potential tendencies really is. If you want to talk of how fast or how slow the reaction begins to go, we'll be looking at that when we treat kinetics. So now we say that the reaction has a delta G standard and biochemical standard of greater than 0 and starts to move forward. So in this reaction, we say that delta G is greater than less than 0, and because it's less than 0, it starts to move forward. We all know from our chemistry that we reach equilibrium with the forward and reverse reaction at the same rate. So as the reaction moves forward, it spends this free energy. Of course, the greater than 0 is spontaneous reaction, so it has a lot of energy. So as it moves forward, it spends this free energy. So I'll just write that down as the reaction. As the reaction moves forward, as the reaction moves forward, it spends, as the reaction moves, sorry about my pen, as the reaction moves forward, as the reaction moves forward, it spends this free energy. It spends, let me just stay close. The reaction moves forward, it spends this free energy. So we know that the free energy has a tendency for the reaction to move forward. What it's telling us is that the reaction wants to be on the right, not the left. So the reaction wants to be on the right, not the left. So as the reaction moves forward, it spends its free energy as it moves towards equilibrium. So moving forward and spending its uh, free energy implies that the reaction moves towards equilibrium. Implies that the reaction moves towards equilibrium. So delta G standard is also a measure of the extent to which a reaction, as written, is not yet at equilibrium. So it means it has more energy to spend as it makes its way to equilibrium. So I'll just take that here if I have the space here. So what that implies, what is the whole of this imply, is that what the whole of this implies is that delta G is also a measure. Delta G standard, let me do it here. Delta G standard is also a measure. Delta G standard is also a measure of the extent. It's a measure of the extent. It's a measure of the extent to which a reaction as written, is not yet at equilibrium. Is not yet at equilibrium. Okay, so it just simply means it has more energy to spend as it makes its way to equilibrium. So we begin to look at another quantitative measure of equilibrium in the next page. Okay. So we want to look now at another quantitative measure that's it. I want to look at another, sorry about that. I want to look at another quantitative measure of equilibrium, and we also know another quantitative measure that is related to equilibrium outside what we just saw of delta G, and that is KEQ, which is the equilibrium constant. So we say the equilibrium constant is another quantitative measure related to equilibrium. It's another quantitative measure related to equilibrium. Okay, so in this type of reaction where we look at equilibrium, we want to look at what KEQ really is, and it tells us what the number KEQ tells us. Is the reaction really going far forward to the right? That is, at equilibrium it is mostly products, virtually no reactants. Or is the reaction going to the left? That means at equilibrium it has a lot of reactants, no products. Or is it somewhere in between? That is what the equilibrium constant KEQ does, and that is what it tells us. And that is what the delta G that we have looked at earlier also do. So for a quick recap, we see that for a quick recap, we see for simple reaction for the reaction. So you have A plus BB, okay, forward and backward reaction. Then you have C plus D. Okay, so the KEQ in this instance, or KEQ in this instance, is equals to the concentration of C, which is product of a reactant, C raised to the power of C plus D raised to the power of D over A, which is a reactant, A raised to the power of A plus B raised to the power of B. So this is the general expression for KEQ. These are the concentrations at equilibrium. This is the general expressions. This is a general expression for KEQ. For KEQ. Okay, and these are the concentrations at equilibrium. So it shows the concentration. It shows the concentration at equilibrium. All right, it shows the concentration at equilibrium. So delta G, which we earlier saw, is the measure of the extent from equilibrium. Delta G, which we earlier saw, is actually the measure of the extent from equilibrium. The KEQ is the measure of the extent a reaction is far from equilibrium. So please get the relationship. Okay, we said that the delta G is the measure of the extent from equilibrium, and the KEQ is the measure of the extent a reaction is far from equilibrium. There have to be two different quantitative measures, but they are measuring the same thing, and there must be a relationship between them, and it's shown below. So I'll do that in the next page to show you the relationship between delta G, which is the measure of the extent from equilibrium, and KEQ, which is the measure of the extent of how far a reaction is from equilibrium. So I'll do that in red. So the relationship is in this equation. Delta G standard goes to minus RT ln KEQ, where R is a constant and is equal to 8.315 joules per mole. Sorry, joules per mole. My pen is starting. So joules per mole, and T is equal to the temperature in Kelvin. Temperature in Kelvin. It is also known as what? Your absolute temperature. Okay, so let's look at our initial reaction with which we started this whole bioenergetics. So we return to, let's return to our initial reaction. And if you recall, it is glucose plus inorganic phosphate that gave us glucose 6 phosphate. So the delta G standard for this reaction is equal to loss 13.8 kilojoules per mole. This is an endergonic reaction. It is not spontaneous as written, it is spontaneous in the reverse. Okay, so this reaction now, because of this delta G standard value, it shows that this is an endergonic reaction. It is not spontaneous as written. It is not spontaneous as written. It is spontaneous in the reverse. Spontaneous in the reverse. Alright, so what this tells us is that glucose under standard conditions, that is standard conditions, we are looking at 1 mole concentration of all the reactants, then this reaction is not wanting to move forward naturally, it wants to move backward. The glucose 6 phosphate, which is the product, is going to break up, it wants to break up into inorganic phosphate and glucose. That's why it is said it is spontaneous in the reverse. So this is not spontaneous as written. In other words, under standard condition, this reaction will not go forward. Want you to note that. Note that under standard conditions, this reaction will not go forward. This reaction will not go forward. That is, which implies that it is not thermodynamically favorable. Which implies that it is not a thermodynamically favorable reaction. It is not a thermodynamically favorable reaction. It's not a thermodynamically favorable reaction. So we're going to look at some calculation on the next page to see how all of this add up. So let's see some calculations. Let's see some calculations. So you see, we're looking at glucose plus pi. So we have a reaction that is not thermodynamically favorable. So it doesn't want to move forward. It is not spontaneous as written. It is actually spontaneous in the reverse. So take note of reaction arrows. So you have glucose 6 phosphate, and this reaction has a delta G equals plus 13.8 kilojoules per mole. Kilojoules per mole. Okay, so if we rearrange this equation to solve for KEQ, so first we want to look at recall our KEQ formula that we gave earlier. So that reaction where we have the relationship between the delta G and the KEQ. So we have it as delta G is equal to minus RT ln KEQ. Alright, so in solving now for KEQ, we want to rearrange this equation. We want to rearrange the equation to solve for KEQ. So rearranging the equation, to solve for KEQ, we have KEQ, alright, KEQ is equal to, is equal to E raised to the power of minus delta G over RT. And when you substitute the equation into what we have E to minus 13,800 all over 8.315, then you have your temperature as 298. Alright, so you notice that the 13.8 kilojoules was converted to joules. So we convert to joules because our arrow value is in joules. And in solving that out, what you have as your KEQ is equal to 3.8 times 10 raised to power minus 3. You also notice the reaction arrows. Okay, arrows of different lengths is written to show what is going on. So you observe that these arrows here have different lengths. So it shows what is going on. A very little product and a whole bunch of reactants is what is happening under this standard condition. So as such, under standard conditions, the KEQ is very small, as you can see. That means it is going to be to the left. That is, the whole idea. From the KEQ, it implies that there is not a lot of product, but a whole lot of reactants. So this is just another numerical measure, and it is related by the R and the T, which is your temperature. All that is happening here is that you have two quantitative measurements to let you know where equilibrium lies for the reaction as written. We'll take another example on the next page, and this time it will be for the hydrolysis of ATP. Just to choose my red. Okay, so let's do another example here. Another example. Okay, so we want to look at the hydrolysis of ATP. So we say ATP plus water gives ADP plus PI. And the delta G for this reaction is equal to minus 30.5 kilojoules per mole. This is a highly exergonic reaction. It is highly thermodynamically favorable. This reaction wants to take place and it wants to move forward. What this means is that you have some 30,500 free energy that you can use to do some kind of work. Whatever that biological work is, whether it is the transporting of some solid across a membrane, whether it's contracting of a muscle, or it's building of a nucleic acid, or building some carbohydrate polymer, whatever it is, for 1 mole of ATP, we have 30,500 free joules, free energy, 30,500 joules free energy that can be used. So we have again written this out. We have rewriting this. We have ATP sorry about that. One word, please. So we look at the equilibrium equation right away. So you have K EQ substituting what we have available. We have E raised to the power minus our delta G here is minus 30,500 joules, converting kilojoules to joules. All right, 30,500 joules all over your R, which is 8.315, and your temperature, which is 298. Solving that out, you have 2.2 times 10 raised to power 5. And this is a very huge number. This is a very huge number. So the fact that KEQ is huge confirms the confirms that there is a whole lot of product in the numerator, very little reactant in the denominator, and that is what is going on. Thus, at equilibrium, thus at equilibrium, thus at equilibrium, we have the following. Thus, at equilibrium, we have the following. We have ATP plus water giving you a whole lot of products, ADP plus PI, and the reverse reaction is this. So this is what the equilibrium looks like. So let's go ahead and see a little bit of example that we consolidate everything that we have talked about. It's equilibrium, free energy, with a typical example that we are going to see several times as we proceed. So from this arrow, like we saw in the other time, we have the forward reaction having a lot of products. As we earlier said, the reaction wants to move forward. So I'll just go ahead in the next page to show you the example. So this is example 1, problem 1, and it reads, when glucose 1-phosphate is incubated at 25 degrees with the enzyme phosphoglucose, the following reaction takes place. Glucose 1-phosphate going to glucose 6-phosphate. The delta G for this reaction is minus 5.4 kilojoules per mole. And if the initial concentration of glucose 1-phosphate is 0.15, calculate the concentration of each species when the reaction has come to equilibrium. So we are given a delta G here. So we are given our delta G here, as we can see. Sorry about that. So as you can see, this is our delta G that is given. We are given our initial concentration. So given our initial concentration, and we see that the delta G of this reaction is minus 7 kilojoules per mole. We are to find the equilibrium concentration. We are given our initial concentration, which is the initial concentration as 0.15 molar. This is essentially an equilibrium problem, and as such, we're going to end up making something called an ice chart. If you remember your general chemistry, the plan is for us to use an ice chart, which means initial change in concentration. So let's just go ahead and solve this problem on the next page. Okay, so from the problem, we are given delta G. We're given delta G minus. We are to find the equilibrium constant, and To do that, we'll need to do an ice. We need to do an ice chart. So ice simply means initial change in equilibrium. Initial change in equilibrium. So it's one of those charts we use to do, we use in general chemistry to track where things start from and where they end up, and then to do calculations based on the equilibrium constant. So we want to quickly bring out a formula again for equilibrium constant. We have delta G standard minus RT IN ln k eq. Rearranging this equation, we have our k eq equal to E, which is for equilibrium, minus delta G over RT. So basically this is our formula. When we go ahead and put these values in, we will have the following. So we fix the values that we were given. Okay, so we have here KEQ is equal to E. So our delta G that we had is minus bracket minus 4,5 converting to joules, okay, over 8.315298. Okay, so KEQ, solving that out, is E raised to R 3.043. As such, KEQ gives you 20.97. So that's our equilibrium constant. So now that we know what the equilibrium constant is, we are going to go ahead and do the equilibrium part of the problem. So let's go ahead and write out our reactions, and we'll do that on the next page. Our reactions, once again, we want to re-establish that we are moving from glucose 1-phosphate for an equilibrium reaction to glucose 6-phosphate. Excuse me. So we are going to have an initial concentration, we are going to have a change in concentration, and we are going to have an equilibrium constant, which is what we are concerned about ultimately. So applying the ice chart, we have I for our initial concentration and your C and your E. So sorry, let me just okay. So we have for your initial concentration, for your reactants, glucose 1-phosphate, we have I equals to 0.15, and for your product is 0. Then you have minus X here. Say your concentration is minus X, and initial change in concentration, and here you have plus X. And your equilibrium therefore is equal to your initial concentration and your change in concentration. So you have 0.15 plus minus X, which is the equilibrium, initial concentration plus change in concentration, and here for your product you have 0 plus X. Alright, so from this chart you can see now that your equilibrium for your reactant is equal to 0.15 minus X, and for your product you have X. So this, which is the equilibrium that we are looking for, are the needed values. These are the needed values. So with that, we now employ it into the solution, into the equation, the reaction equation. So we have KEQ, I could do that here. So we have KEQ is equal to your X, your product, over your reactant, which is 0.15 minus X. And all of these is equal to 20.97 as earlier calculated. So we can solve for X. So it implies, so this whole equation implies product over reactant at what? Equilibrium. The whole of this equation implies the product over the reactant at what? Equilibrium. So X is what we are looking for. So to solve for S, we bring out S, making the subject of the formula. Then we have 20.97 brackets 0.15 minus X. So if we go ahead and do our algebra, what we have is X is equal to 0.1432 molar. And that is the equilibrium constant for glucose 6-phosphate concentration. So the equilibrium constant for glucose 1-phosphate concentration, we have gotten this for glucose 6-phosphate concentration. So we now look for the equilibrium constant. Implies look for the equilibrium constant for the this equilibrium concentration for glucose 6-phosphate. So we now look for the equilibrium concentration, not constant, for glucose 1-phosphate, which is the reactant. And from our ice chart, glucose 1-phosphate, according to our ice chart. So from our ice chart, you have your glucose 1-phosphate concentration. Glucose 1-phosphate concentration is equals to 0.15 minus x. So if you apply x from what we have been given and x from this concentration of equilibrium concentration of glucose 6-phosphate is 0.15. So you just apply that. So you have your equilibrium concentration. I'm sorry about that. Like this. So equilibrium concentration for glucose 1-phosphate is now equal to 0.15 minus 0.1432 molar, and what that gives you is 0.0068 molar, and that is the concentration, equilibrium concentration for glucose 1-phosphate. Thus the final answer, I'll do that in blue. Let me go back to blue. And let me just do this in the next page too. Thus, the final answer for the equilibrium reaction equation or problem is x is equal to 0.1432 molar, and that implies the concentration of glucose 6-phosphate and 0.15 minus x, which is your reactant, is equals to 0.0068 molar. 68 molar, and that's for the concentration of glucose 1-phosphate. So we started with the delta G in this whole reaction, and this is actually the whole of this now is your final answer. Sorry about that. Final answer to the problem. So we started with the delta G, we converted to KEQ, we did the equilibrium problem and the answer confirms that most of the glucose 1-phosphate has been converted to glucose 6-phosphate. As you can see, the product is far higher than the reactant, so it has been converted to product. There is virtually no leftover for glucose 1-phosphate, which is the reactant, as it is 0.006. Thank you very much.